Hi, everyone. Let's get started on problem 3.79 from Young and Freedman's University Physics textbook. Thank you so much for all the support lately. And yeah, thank you so much for watching my videos. So let's get started on this question. A projectile thrown from a point P moves in such a way that its distance from P is always increasing. Find the maximum angle above the horizontal with which the projectile could have been thrown. Ignore air resistance. So to understand this problem a little bit better, we can get started with a diagram. And in this diagram, I'm just going to draw a typical projectile trajectory. So if we start from this point and we work to this point, we see this arc shape. And really what this question is saying is we want P to always be increasing if this point is P. So by that, we mean that at any point, so at point A, B, C, D, E, right, F, we want this projectile to be thrown so that these red lines at every point are always increasing. And if you think, well, doesn't that always happen? No, and I can prove that with a counterexample. So in another scenario, if we have a projectile that looks a little bit more like this, we can see here that if we have points A, B, C, D, let's say E and F. Oh, let's actually make this F and we'll make this G. Okay, so yeah, at point A, B, C, and D, we can see that this distance is always increasing from P. But then if we get to point E, we can see that E is actually smaller than the distance from P to D, right? So PE is greater than PD, and that's not what we want. So we know that we're looking for this scenario. But what exactly are we looking for in this problem? The maximum angle. And the reason we're looking for the maximum angle is that because in any projectile that has a really small angle, or let me just draw that a little bit better. If we have a projectile that looks sort of like this, where we have a very small angle, theta right here, we know that this distance is always going to be increasing. But as this angle gets larger, we have this scenario right over here, right? And in this scenario, we see that the points A, B, C, D, E, F, we see that it gets larger at first, but then smaller. The distances between point P and other points in the projectile trajectory. And so we want to find the maximum angle above the horizontal with which the projectile could have been thrown. Okay, so to do that, I'm going to just draw the projectile again. And if we draw the projectile again, I'm going to just do something that looks like this, in which we're going to assume that at every point, starting from P, starting from P, the distance is always increasing. Okay, so we see that at this point, it's always going to be increasing all the way till the end. And if we can see this in the beginning of the question, but it says that it's a calculus question. And in calculus, we know that if we want to get the distance from any point to P, or P to any point, we know that it's going to be, we can use Pythagorean theorem for that. So we can do this. We can, for example, if we have this green line right over here, we know that this distance, P to this point, so let's just call this like X, right? So let's say that the distance from PX is D, right? And we know that D squared is equal to X squared plus Y squared. So if this is X and this is Y, we know that, oh, actually, maybe I shouldn't have used x right over here. Let's just say that this is, let's say like f. So pf is equal to some distance, and then we have x squared plus y squared is equal to that d squared according to Pythagorean theorem. And how do we get x and y? Well, we know that from projectile motion, this is going to be fairly typical of all the projectile motion questions. So we know that if we, I'm just going to draw this triangle here again. So this is d, it's x, and this is y. X, and this is going to be some angle, let's call it theta. So we know that x is going to be v naught cos theta t, because here we're just using distance is equal to speed times time, right? And then in y, we know that there's actually going to be an acceleration component included here. So it's not just, so distance is not just going to be some constant speed and time, there's also acceleration involved. So we actually have to use one of the 5 kinematic equations. And what we get is v naught sine, sorry, I actually used, while working the problem on my own, I used alpha. So sine theta t minus half of gt squared, because we know that there's acceleration due to gravity working on it, right? And this is just the formula v naught t minus half at squared is equal to d. That's really where just I got this formula from, but I just customized it so that it follows the problem that we want it to follow. Okay, so once we do that, we know that d squared can be rewritten as x squared and y squared. So v naught squared cos squared theta t squared plus v naught squared sine squared theta t squared plus 1/4 g. Oh, actually, let me just rewrite that all out. Let me just actually erase this, and I'll just draw this a little bit smaller in the top corner. Right here. So if we have, oh no, okay. This theta, and this is x, and this is y, and this is d. I'm gonna rewrite d squared as x squared and y squared. So d squared is equal to v naught squared cos squared theta t squared plus v naught squared, v naught squared sine squared theta t squared minus or plus 1/4 g squared t to the 4 minus gt squared v naught sine theta t, right? And if we collect like terms, we can just do v naught squared cos squared plus sine squared theta, right? Because we can use that identity. Sorry, I forgot the word. I forgot it's property or identity. And in this identity, we can, oh, let's just first finish up the simplification. Okay. Well, this we know is 1. So we're left with v naught squared t squared plus 1/4 g squared t to the 4 minus g t to the 3 v naught sine theta. Okay, and that's d squared. Sorry. And I'm just double checking with my notes to see if that's the same thing that I got. And it is. Yes, it is. Okay. So now one thing that we have to recognize in the problem is that they're asking us we want to see the projectile is thrown from a point P, and it moves in such a way that the distance from P is always increasing. So oh, sorry, just going to erase this top portion. So we know that if this distance from, so if we see that if this distance, sorry, just got a text, distracted. Okay, so in this problem, we noticed that if I'm so sorry, I'm getting a text. Just gonna pause this. So sorry about that. I just turned on my do not disturb so that I'm focused on this problem. Okay, so we know that according to calculus, if we want the distance to always be increasing, we know that the distance is actually changing over time, right? So at some time, some earlier time, okay. So at some earlier time, at this point, right, the distance is going to be some distance, right? And then at a later time, the distance is going to be different. So if we actually differentiate with respect to distance, let me just get back to my green pen. So we have to differentiate distance with respect to time, and that's going to give us the distance that is changing over time, and because that's what we want in the question. And since we always want it to increase, right? Oh, actually, I wrote that wrong. Let me just rewrite that. So we're gonna take the derivative of distance squared with respect to time, and we're gonna make sure that that's always greater than or equal to 0 because we want it to always be increasing. Okay. And if we take the derivative and we solve for t, then we can figure out this angle situation. Okay. And let me just erase this portion right over here. So we're just left with d squared at the bottom because that's really what's important. Okay, so d squared, we want to take the derivative of that, sorry, with respect to time. Okay, and I'm just going to double check with my notes to make sure that that is consistent. Let's see. Okay, that looks good. That, yeah, okay. And so now what we're going to do is we're going to set this equal to 0. So we want 0 is equal to 2v naught squared t plus g squared t to 3 minus 3gt squared v naught sine theta. Okay, and now we can recognize that we can actually cancel out one of these t's, right? And we get 0 is equal to 2v naught squared plus g squared t squared minus 3gt v naught sine theta. Okay, well, if we want to solve for t, what we can do is we can use the quadratic equation. And when we use the quadratic equation, sorry, just double checking again. Okay, yeah, we're good. Okay. So when we use the quadratic equation again, we're gonna get this. We're gonna use different color, minus, oh, let me just write this so that it's in correct format. So we have our A first, then we have our B term, And then we're going to use the quadratic formula. So we get negative b, which is negative 3g v naught sine theta. Oh, looks like I don't have space. Sorry, I'm just going to rewrite it right over here. Okay. So negative 3g v naught sine theta plus minus b squared. So we're going to have 9g squared v naught squared sine squared theta minus 4ac, so minus 4, a is g squared, and then c we have 2 times b naught squared over 2a. Oh, it's not good. Okay, there we go. Not good. Okay. Over 2a, which is 2g squared. Okay. Well, remember that if we want to solve this, we want a real time. And if we want a real time, then this term right over here also has to be real. So notice that we can actually solve for what theta has to be for this to even be real in the first place. And we can do that right over here at the top. Okay. So we're going to solve for 3g v naught sine theta squared minus 4g squared 2 v naught squared. Okay. And we can solve, and this can be real if this is greater than, or if this entire discriminant is greater than or equal to 0. So let's set it equal to 0, because we can't have negative and we can't have imaginary time for this to happen. So we want it to be a real solution for t. So we're going to have 9g squared v naught squared sine squared theta is equal to 4 or 8g squared v naught squared. Well, we can just cancel out g naught squared and v naught squared, and we're left with sine squared theta is equal to 8 over 9. And I'm just going to grab my calculator to plug this in. All right, brought my calculator and I plugged it in. And the answer that I'm getting is theta is equal to 70.53 degrees. Okay, so what is this angle? This is the maximum angle above the horizontal for which the projectile could have been thrown if we always want the distance to be increasing from p if we always want the distance to be increasing from p at every point in time in the future. Okay, so that's our solution, 70.53 degrees. This was a little bit of a tricky problem, but here we have it here we have the solution. So if you have any questions, please feel free to send me an email or leave a comment. And that's the end of this video. Thank you so much for watching. And if this was helpful, please don't forget to like and subscribe for the future. See you next time. Bye.